Welcome to This Explainer, where we're going to show you exactly how to tailor your Cambridge physics answers to fit perfectly, starting with one of the most high-stakes topics out there, radioactivity safety. Now, I want you to think of yourself as a master fashion designer for a moment. Stick with me here. You wouldn't just throw a massive pile of raw, uncut fabric at a client and hope it magically fits them, right? Of course not. You measure, you cut, and you stitch every single seam with absolute precision. Well, that is exactly what you need to do with your physics knowledge in the exam hall. Today, we are focusing on one of the most critical and honestly most frequently tested areas across all the major syllabuses. I'm talking about 0625, 0651, 0652, 5054, and 9702. We're diving deep into the effects of ionizing radiation on living things, stuff like cell death, genetic mutations, and cancer, and we're pairing that with the precise, non-negotiable safety precautions required for moving, using, and storing radioactive materials. By the time we finish this explainer, you're going to know exactly how to weave your knowledge together so tightly that there are absolutely no loose threads left for the examiner to pull.
Okay, let's dive right into this by stepping directly into a senior examiner's mind to see what truly separates an average run-of-the-mill paper from top-tier mastery. You see this quote? It is absolutely not an exaggeration. The difference between a B and an A-star in physics often comes down to how well you understand radioactivity safety. And you might be wondering why? Because this specific topic demands way more than just rote memorization. Literally any student can memorize the fact that radiation is dangerous, but an A-star candidate, they understand the deep, complex causal relationships. They know exactly why alpha particles, which are highly ionizing but easily stopped, require completely different handling protocols than highly penetrating gamma rays. They understand the inverse square law of distance, the dense electron structure of lead shielding, and exactly how ionizing radiation literally strips electrons from atoms in human DNA, leading to those dangerous mutations or cancer. Examiners use radioactivity questions as a massive filter to see who truly understands the real-world application of physics.
So, here is our structured roadmap for today's session. We'll start with the challenge, move into core concepts, build out your procedural framework, run through a quick interactive workshop, and finally reveal some critical examiner insights. Let's get moving.
Act 1. The challenge. We're looking at superficial breadth versus analytical depth.
Let's look at a real Cambridge physics past paper challenge where two students, who we'll call Alex and Sam, totally failed to hit the required academic benchmarks. Imagine you're sitting in the exam hall and you see a massive 6-mark question asking you to evaluate safety precautions for a highly active gamma source in a hospital setting. Take Alex's approach first. Notice how Alex relies on superficial breadth by just listing biological effects. Alex writes a total brain dump. Radiation is very bad, it causes cell death, it causes DNA mutations, and it causes cancer. Okay, sure, factually true, but it completely ignores the actual physics of the hospital context. There is absolutely no mention of the specific properties of gamma radiation or the actual precautions needed. Now, look at Sam's approach. Sam sees the word precautions and goes into a panicked rush, completely missing the logical structured reasoning the command words demand. Sam frantically scribbles, reduce time, increase distance, use shielding. Again, factually correct, but where on earth is the explanation? Why increase the distance? Why use shielding? Sam completely failed to link the safety protocol to the biological threat. Both of these students left massive gaping holes in their answers. They brought the raw fabric, but they completely failed to tailor the suit.
Moving on to Act 2, Core Concepts. Let's look at how we actually master this and transition into our strategy reveal.
Before we continue, subscribe to our YouTube channel Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, to bridge that huge gap between a superficial answer and an analytical one, we need to establish the exact theoretical architecture you need. We use the Peel framework: point, evidence, explanation, link. You absolutely must memorize the causal relationships shown here, directly linking the biological dangers to the procedural safety precautions. When you're asked about radioactivity safety, you can't just state a loose fact. You have to provide evidence, explain the actual physics behind it, and link it directly back to the context. Think about the biological effects. Ionizing radiation enters the body, it ionizes cellular water molecules, creates free radicals, physically damages the DNA, and causes cell death, mutations, or cancer. That's the threat. Now look at the physics toolkit to stop it. We reduce exposure time to mathematically limit the total dose absorbed. We significantly increase distance, using long tongs or remote-controlled robotic arms because the intensity of radiation drops off incredibly sharply the further you get from the source.
And we use shielding, like heavy lead-lined aprons or thick concrete, because those incredibly dense materials absorb the ionizing particles long before they can reach human tissue. You must mentally lock these two concepts together. If you talk about cancer, you better be talking about shielding.
So the absolutely crucial point here is that to get that A star, you must integrate these precise definitions with cross-topic connections. The Cambridge syllabus explicitly states that top-performing students exhibit connected, conceptual understanding that is completely transferable to unfamiliar contexts. What does that mean? It means the exam might throw an unfamiliar scenario at you, maybe a nuclear submarine, a commercial food irradiation plant, or a deep space probe powered by radioisotopes. It doesn't matter. The underlying physics doesn't change, only the application does. If you know how gamma rays interact with dense matter, you can apply that to a submarine hull just as easily as a hospital wall.
Let's move into Act 3, the transformation, and look at the actual physics procedural framework you need to use.
Instead of panicking and rushing like Sam, you need to follow this standardized sequence to transform your answers. This ensures you apply the correct formats and terminology every single time, without fail. Step 1. Deconstruct the question. Literally circle the command word. Is it state, describe, or explain? Because explain means you need that full peel framework. Step 2. Extract relevant data. You have to ask yourself, is the source alpha, beta, or gamma? What exactly is its half-life? Step 3. Select the analytical framework. If you're dealing with a highly penetrating gamma source, your framework absolutely must include thick lead shielding and remote handling. Step 4. Execute with clear notation. If there is any calculation required for, say, safe exposure time, you have to show you're working out clearly. And Step 5. Present with the correct terminology. Please never just say radiation kills you. It's not scientific enough. Say ionizing radiation causes cellular damage and DNA mutations. This kind of precise, tailored language is exactly what unlocks those top-tier marks.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Now, look at this comparison. See how the analytical depth on the right completely obliterates the superficial answer on the left by locking into the specific context? The left side is exactly what our panicked student Sam wrote. Use shielding to stop cancer. It's incredibly vague. It leaves massive loose threads. The examiner is literally sitting there asking, okay, but what kind of shielding? Why does it stop cancer? What is the actual physics mechanism here? Now look at the beautifully tailored answer on the right. In this specific context, using lead shielding prevents mutations and cell death by absorbing ionizing radiation. Wow! It identifies the exact material, lead, it links it to the specific biological effect, mutations and cell death, and it explains the actual physics mechanism, absorbing ionizing radiation. That is a perfectly tailored, no loose threads answer.
All right, Act 4. Let's dive into our interactive workshop, where you'll apply these interpretation skills under the real pressure of a ticking clock.
For Challenge 1, the data scan, imagine you have exactly 60 seconds to process incredibly complex information about the safe moving and storage of radioactive materials. Picture a complex data table in front of you showing 3 different radioactive isotopes. Isotope A emits heavy alpha particles with a half-life of 4 hours. Isotope B emits beta particles with a half-life of 5 years. And isotope C emits intense gamma rays with a tiny half-life of just 10 seconds. Your job? Extract the core trend right now. Which one requires immediate thick lead shielding for transport across a lab? And which one requires long-term secure underground storage? You have to interpret these relationships in seconds. Isotope C needs the heavy lead because gamma is highly penetrating, but only for a very short time due to that fast 10-second half-life. Isotope B, however, needs secure long-term storage because of that massive 5-year half-life. Drawing these evidence-based conclusions rapidly is a non-negotiable skill for the exam.
Let's move to Challenge 2. Find the flaw. Look closely at this problem-solving attempt and tell me, are they failing to identify limitations or missing alternative interpretations? Imagine a student wrote this paragraph. To safely transport the highly active gamma source across the laboratory, the technician should use long metal tongs to increase distance and wear a thick aluminum apron to block the radiation, ensuring exposure time is kept under 5 minutes. Okay, what is the critical flaw here? Think about it for a second. Have you spotted it? The flaw is the aluminum apron. Aluminum is completely ineffective at blocking highly penetrating gamma radiation. It only blocks beta particles. Gamma rays will pass right through that aluminum like it's not even there. The student applied the completely wrong physics principle to the specific context. And guys, this is exactly how candidates bleed marks in the exam hall, by just not verifying that their safety precaution actually matches the specific type of ionizing radiation they're dealing with.
Now, for Challenge 3, speed writing. You need to use these 4 rules to evaluate evidence quality before the timer runs out. When a Cambridge 0625 question asks you to compare the safety precautions for, say, an alpha emitter versus a gamma emitter, you absolutely must use comparative connectives. Words like whereas, however, or in contrast. First, you state the similarity. You must state that both require limiting exposure time to prevent cell mutation. That's your baseline similarity. However, an alpha emitter is highly ionizing but very weakly penetrating, meaning internal contamination like breathing it in is the primary risk, so respiratory masks are absolutely crucial. In contrast, gamma is highly penetrating but less heavily ionizing per collision, making external exposure the primary risk, which requires dense lead shielding. You see what we did there? You support each point with evidence and you draw a clear conclusion. That is exactly how you execute a flawless Peel paragraph under the pressure of a ticking clock.
Finally, let's head into Act 5, Evaluation and Examiner Insights, where we learn how to avoid the top traps.
This is basically the ultimate cheat sheet. The principal examiner reports highlight exactly where students bleed marks year after year. Let's look at the top 3 warnings. Warning number 1, using the wrong approach for the wrong context. We literally just saw this with the aluminum apron for gamma rays. It's a classic mistake. Warning number 2, forgetting to check your format and presentation. If a question specifically asks for 3 distinct safety precautions, for the love of physics, do not write a single massive unreadable block of text. Use bullet points, be structured, make it easy for the examiner to give you points. And warning number 3, answers not specific to the context given. If the exam prompt is about a worker in a nuclear power plant, don't start talking about hospital X-ray precautions. You must tailor the fabric to the specific client. If you just give a generic, memorized brain dump about radiation safety that completely ignores the prompt, the examiner simply cannot award you top marks.
And listen up, because this is arguably the most critical strategy you can deploy, the method mark strategy. Execute your analysis with crystal clear working out so you get credit for your thought process. Let's say you're calculating the safe exposure time based on a complex half-life decay curve. You accidentally misread a tiny number on the graph, and so your final calculated time is completely wrong. If you just wrote down that final wrong answer, you get a 0, nothing. But if you clearly wrote down the formula, showed your exact substitution, and documented your logical steps, the examiner can totally award you method marks. They will look at your process and think, okay, this student completely understands the physics of radioactivity safety. They just made a minor arithmetic error under pressure. Always, always show you're working. It is literally the ultimate safety net for your grade.
This final blueprint guarantees marks by forcing you to identify the given information, break it into logical steps, check for reasonableness, and make completely justified recommendations. You deconstruct those command words, you solve using the PEL framework and the correct physics terminology, and you evaluate to ensure your answer actually makes logical sense within the real-world context of the question. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
So, take this master examiner's mindset directly into your very next practice session. Apply the framework without leaving a single loose thread. Think about how you'll approach your next past paper. Are you going to rush in blindly like Sam, or do a messy brain dump like Alex? Or are you going to be the master tailor, carefully deconstructing the context, weaving together the biological risks with the absolute correct physics principles? The choice is entirely yours, but the tools are now in your hands. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the exams. Your Cambridge success starts here. Keep analyzing, keep practicing, and I'll see you in the next one.